Number 11, let W be the set of all solutions of the equation x plus y minus z equals to 0. And we need to show that W is a subspace of R3, and then we need to find the dimension of W. Okay, so what is W? Okay, ask the question first. What is that set? The set W is not the equation x plus y minus z. Think about it. It's the set of all solutions. Okay, so that means W is the set of all x, y, z. Okay, all x, y, z, but with a specific condition. Okay, what is the condition? The condition that x plus y minus z, whatever they are, they need to obey this equation. So if they need to obey that equation, it's not all x, y, and z, okay? It's some of them from R3, and not all of them will obey that equation. So that is the set W. How do we show that it's a subspace? Well, we need to check those two conditions, right? First is if you pick two vectors in this set, and if we add them, is the addition still in that set? And second, if we pick a vector and we multiply by a scalar, is still the multiplication is still that in that set W? If those two conditions are satisfied, then yes, W is a subspace. If it's a subspace, then it is a vector space, right? So we can find the dimensions. We need to find the basis for it. So let's pick two vectors in W and then do the addition and the scalar multiplication. Okay. So I picked two vectors in there. Now if they are vectors from W, then they need to obey this equation here. Okay. So we have the following. We have that x1 plus y1 minus z1 is 0 because this vector is in W. Also, same thing, x2 plus y2 minus z2 is in W. Oh, I mean, x2, y2, z2 is in W, therefore it satisfied, the vector satisfied this equation. How do we show now if I add the two, here's the new vector, if I add the two, how do we know that the addition is in the set? So how do we know that? Here's the addition, x1 plus x2, y1 plus y2, z1 plus z2. Okay, I added two vectors. How do we know that this vector here is in W? Well, to know that if it's in W, we need to check whether this new vector here satisfies this equation. Okay, so let's see how we do this. Well, plug these three values in the equation here and see if it works, right? So, does see the first this is the new vector. Okay, this is your x here, right? This is your y, and this is your z. This is your x, y, and z. So if I add this plus this minus this, do I get 0? Does x1 plus x2 plus y1 plus y2 minus z1 plus z2 equals to 0? The only way to know this is to work with these two here, these two conditions that we found, right? Well, it's easy if you add these two equations. You can add the two equations. add the two equations, x2 plus y2 minus z2 equals to 0. If we do that, then that's what we get. Right? x1 plus x2 plus y1 plus y2 minus z1 minus z2, and on this side is 0. So yes, this is okay. So the sum, this sum here, is in W. Now what we have to do is to check the second condition. Now here's the question. Let's organize this a little bit. So this was number 1. Add the two vectors and see if that is in W. Here's number 2. Let's multiply by a scalar, right? So multiply C times one vector. Which is cx1, cy1, cz1. Alright, is this in W? How do we know? Well, we need to check the same thing. If this is my new vector, right? X, y, and z. Does x plus y minus z equals to 0? If it does, then that scalar multiplication is in here, is in W. So does cx1 plus cy1 minus cz1 equals to 0? How do we know? Well, let's pick the equations again. We have an equation that is from the first vector, because the first vector is in W, right? The x1, y1, z1 is in W. It satisfies this. So we can multiply. Right, multiply both sides by the scalar. So you get cx1 plus cy1 minus cz1. 0 times the scalar is 0. So yes, it does satisfy, right? So this vector here is in W. The conclusion is W is a subspace of R3. Okay, and then the final question here is in number 11. Find the dimension of W. Okay. To do that, we need to see how the vectors in W are written. Okay. So I know that this is a subspace. Now I need to pick a vector here and see how it's written. Okay, so here this is how it's written, x plus y. They have to obey this equation. So we need to see how does x, y, and z look like. The only way to know how they look like is to solve this equation, right? You want to know who the x, y, and z are? Solve this equation here. How do we solve this equation? Well, it's just a system with one equation, right? So let me write this here. To find the dimension of W, we need a basis for W. So let's look at how the vectors are in W. So vectors in W need to obey this equation here. So let's solve it. That is 1, 1, negative 1, 0. Okay? That's a system of equations. Now it has 3 variables. So if we don't have more equations, This really means that the other lines are 0, 0, 0, right? So that equation by itself, it's this system. So this means this z, we don't have c's here. We are trying to find the x, y, and z, okay? We are finding what x, y, and z are. So this says that z can be any number. Okay, let's say s, okay, a parameter. And this here says that y can be any number. Let's put t. And then this says that x is, if I move these two terms to the other side, x is negative y plus z. Well, that means that this is negative t plus s. So that's the solution. I mean, it's infinite number of solutions, of course. So here we have it. X, y, z is negative t plus s, t, and s. Okay, now let's split this so we can see what vectors are spanning W. So split that into two vectors, one with the t and the other with s. Okay, and then factor t out. And factor s out. So here it is. Now we can see how what vectors are generating W or spanning W. These are the two vectors, negative 1, 1, 0, and 1, 0, 1. Those are the two vectors that are spanning W. So we see here that these two vectors span W. To find the basis, all we need to know is if these two are linearly independent. And they are. You check. Okay, I'll let you do this. Check that they are linearly independent. Okay? So I need to do this. So therefore, they form a basis. Negative 1, 1, 0, 1, 0, 1 is a basis for W. So dimension of W is 2 because there are two vectors in the basis.